All right, good afternoon, guys. So we're into the last part of the course now, and that's on graphs. And last class, we spent a bunch of time defining things about graphs, different types of graphs, how we can store graphs. What I'd like to talk about today is some properties that graphs have, and along the way, we'll learn some new terminology for working with graphs. So the first thing I'd like to talk about today is the idea of adjacency and degree. So adjacency and degree. So we've already sort of talked about adjacency, although I didn't formally define it. So let's say we have a graph G. Remember, a graph G is an ordered pair. The first thing is a set of vertices, and the second thing is a set of edges. The idea of being adjacent means that two vertices are adjacent if they're connected by an edge. So if there's some edge that has those vertices as endpoints. So two vertices are adjacent. Another way you could say that is that they are neighbors. I'll use those sort of interchangeably. In the graph G, if U and V are endpoints of some edge in G. So in particular in E, which is the edge set of G. Okay, so that's what it means to be adjacent. If an edge E connects vertices U and V, then we say E, the edge, is incident on U and also on V. So you'd say E is incident on U, or E is incident on V, or you might say it's incident with U, or incident with V. Okay? So vertices are adjacent to vertices, and edges are incident on vertices. All right, so now that we have both of those, we're ready to talk about the degree. So the degree of a vertex in an undirected graph, so I'm only going to talk about undirected graphs for now. I'll get to the directed case in a second. In an undirected graph, the degree is the number of edges incident with it. The number of edges incident with it, or on it. Right, means the same thing. And we have a special notation for this. It's deg V, for degree of V. So deg of V. One little catch is if you have a pseudograph, that means you could have self-loops. And in that case, it contributes 2 to the degree, because it's somehow both leaving and entering that same vertex. So if a self-loop is present, it gets counted twice in this. It's incident, that edge is incident on the vertex twice. And this might seem weird, that we would count it that way, but this comes in handy when we're talking about other things later, so that's why we do it. So let's do a little example to get the hang of this kind of thing. So I have a graph that looks like this. I'll call this A, B, C, D, E, F. and I have an edge from A to B, an edge from B to C, a self-loop at C, an edge from E to D, maybe another edge from E to D, maybe another edge from E to D, an edge from E to C, and an edge from B to D, and maybe I have two edges from A to E. Okay, so this is an example of a graph. And notice that F is off on its own. It doesn't have any edges incident with it. All right, so let's work out some of these degrees. What is the degree of A? How many edges are on it? Yeah? 3, right? There's one right here, there's one right here, and there's one right here. So the degree of A is 3. All right, what about the degree of B? It's also going to be 3. There's one right here, and right there. So the degree of B is also going to be 3. The degree of C is going to be what? 4. There's one here, and this self-loop is counted twice, because you can kind of see it as leaving the vertex twice in some sense. So the degree of C is 4. The degree of D, what's the degree of D going to be? So I have 1, 2, 3, 4, so the degree of D is 4. The degree of E is going to be what? 6. 1, 2, 3, 4, 5, 6. And finally, the degree of F, 0, right? There's no edges that are incident on F. All right, so that's what all of those things are. Does anyone notice anything about this graph after I made all these marks on it? So I made a mark every time I counted one of those degrees. What happened to the graph? It gets messier, sure. Yeah?
Each line gets 2 arrows?
Each edge, so each line in the graph, gets exactly 2 arrows on it. So these arrows aren't the same as a directed graph. This is just me keeping track of counting. So I made an arrow every time I increased a degree by 1. And now I know that there's 2 arrows on every single edge. So if I sum up all of the degrees in this graph, what am I going to get? Well, in this particular graph, I get 6 plus 4 is 10, 14 plus 3 is 17, plus 3 is 20. So the sum of all those degrees is 20. How many edges do I have in this graph? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that kind of makes sense, right? Because I increased the degree by 2 for every single edge. So the sum of the degrees should be twice the number of edges. And in fact, that's exactly what we have. The sum of all the degrees is 20, and there are 10 edges. There's nothing special about this graph. That happens for every single graph. Can anyone take any guesses to why? Why does this happen in general?
For each edge there are 2 vertices.
Right, every single edge is incident on exactly 2 vertices. There's no edge that doesn't lead anywhere, and every edge is on at least 1. So that means that every edge contributes 2 in my sum of these degrees. This is an important result that comes in very handy. This is called the handshaking theorem. And the handshaking theorem says that this observation, really does hold for every graph. So if G equals V comma E is a graph, then I need some way of saying that the sum of all the degrees is twice the number of edges. And because I've paid very close attention in this course, I know a very concise way of saying that exact thing. The sum of all the degrees. So the sum over all vertices V in my set of vertices of the degree of V is equal to 2 times the size of the edge set. So this summation notation, we didn't see it exactly like this, right? We saw something similar to this when there some integer lower bound and upper bound. But the same thing works for this. And if you're familiar with Python, this is really familiar, right? If we were in Python, we would say something like for V in V, sum up the degree of V. We can use the same notation here. So this is handy. So the way you read this is you take every single vertex in V and add up this quantity here, and this quantity is just the degree of the vertices. And when you do that, you get twice the number of edges. So does this make sense? This is the handshaking theorem. This comes in very handy. Sometimes you know something about the degrees, but you don't know something about the number of edges. This lets you get from one to the other. All right, so everything I was just talking about applies to undirected graphs, but you might want to have a directed graph and some notion of degree there. Well, then you have to split it up into the edges that are coming into a vertex and the edges that are leaving a vertex. Both of those are sort of their own thing, right? So we split up degree into 2 degrees. The in degree, the number of incoming edges, and the out degree, the number of outgoing edges. So for a directed edge u comma v, so when I say u comma v, I mean starting at u and going to v. All right, that's what that means. We call u in the initial vertex, and we call v the terminal vertex or the end vertex. Either of those is fine. So it's the terminal or end vertex. Okay, and we have this notion of degrees in this case as well. So let me define those. The number of incoming edges to V, which is the number of edges where V is a terminal edge, or where V is the terminal vertex, sorry. So the number of incoming edges to V, which is really saying the number of edges where V is the terminal vertex of that edge, is called the in degree of V. It's the number of edges going into it. And we have notation for this. So this is deg with a minus sign. Of V. All right, and then we have the other way around as well. So the number of outgoing edges from U, which is really just the number of edges where U is the initial vertex, is called the out degree. Of U, and is denoted deg plus of U. So minus is for incoming, plus is for outgoing. Not completely sure why we chose those particular symbols, but that's what everyone uses, so that's what we'll use. So let's take a look at this. Let's do an example with this. I'll do something similar to the last one, but I'll direct some of those edges. So A, B, C, D, E, F. Maybe A goes to B, B goes to C, C goes back to B, C goes to D twice, D goes to E, and E goes to B. Let's just say. All right. So let's figure this out. What is the in-degree of A? 0, right? Nothing leads into A. So the in-degree of A is 0. What about the out-degree of A? 1, right? There's one edge out of A, it leads to B. All right. What about the in-degree of B? Right? So I have one edge coming from A, one edge coming from E, and one edge coming from C. So it's 3. What about the out degree of B? 1. I have one edge that leads to C. Okay. The in degree of C is going to be what? Just 1. I have an edge coming from B. And what about the out degree of C? 3. I have an edge going to B, and then 2 edges going to D. So 3. All right. What about the in degree of D? 2, right? I have 2 edges leaving C that enter D. So my in degree is going to be 2. What about my out degree from D? Just 1, it's the edge that goes to E. The in degree for E is going to be what? 1. And the out degree for me is going to be 1. It leads to B. And then finally, the in degree for F, 0. And the out degree for F is also going to be 0. Okay, so let's see what happens if we add these things up. 3 plus 1 is 4, plus 2 is 6, plus 1 is 7. 1 plus 1 is 2, plus 3 is 5, plus 1 is 6, plus 1 is 7. So if I add up all of the in degrees, I get 7. If I add up all of the out degrees, I get 7. What's probably going to happen in general? Right, those are going to be the same, because every edge contributes 1 to someone's in degree and 1 to someone's out degree. What about something like this? Let's say I added a self loop from E to E. What would happen to E's in degree? It would increase by 1, and what about its out degree? The exact same thing would happen. So having self loops doesn't change anything, except it no longer adds 2 to the degree, it adds 1 to the in degree and 1 to the out degree. Is there anything special about the number 7? Yeah, if I count the edges, I have 1, 2, 3, 4, 5, 6, 7 edges. And that's not a coincidence, right? Because I said every one of those edges contributes 1 to someone's in degree and 1 to someone's out degree. And therefore, in general, if we have the sum of all vertices in V of the in degree of V, that's exactly the same as the sum of all vertices in V of the out degree of V, which is exactly the same as the number of edges. Does that make sense? Okay, so these are the first couple of results that we've seen that have something to do with graphs, right? These are our first couple of examples of properties graphs have that we can prove about them. Now, I haven't done a full proof of these, but you guys explained to me what was going on, so you obviously understand why these things are true, even if we haven't done a full proof. Any questions about adjacency or degree? All right. So the topic I'd like to talk about next is a few examples of special graphs. So it turns out there are a few kind of general types of graphs that we give special names to because they come up frequently. So it's nice to have some name to talk about them. So there are a few types of graphs with special names. So there's lots of examples of these. The first example I want to talk about is called the complete graph. So that's the first example. The complete graph on n vertices. And this is denoted k sub n. K for complete. All right, so the way this graph works is every vertex in the graph is connected to every other vertex in the graph. So somehow this has the largest number of edges you can have while being a simple graph. So I'll draw those out. Well, first I'll write down what the definition is. It is n vertices where each is connected to all others. All right, so K1 looks like this. It's one vertex, and there are no edges because I want it to be a simple graph. So K1 is just a vertex. K2 is two vertices, and each vertex has to be connected to every other vertex, so I have one edge that connects those two vertices. K3 is the complete graph on three vertices. So I draw it like that. And I connect each vertex to every other vertex. So I have three edges. At this point, I'll note that it doesn't matter how I draw the graph, right? It would be just as correct to draw my graph like this. The important thing isn't how the graph looks, it's what the connections look like. Right? I don't care if this is an equilateral triangle. The thing I care about is that the first vertex is connected to the other two, the second is connected to the first and third, and the third is connected to the first and second. That's the important thing. Right? It doesn't matter how we draw it. So that's an important thing to keep in mind about graphs. If you are interested in how the graph is being drawn, that is another field of computer science called graph drawn, and it's interesting in its own right, but it's not what we're doing here. So that's K3. Next I'll do K4. That's four vertices, and each vertex has to be connected to every other vertex. A common mistake is to think the pattern is this, but of course this is not K4 because each vertex is not connected to every other vertex. I need to add this edge, and I need to add that edge. And that is K4. And I'll do one more, just so we get the hang of it. K5 is five vertices, and each vertex is connected to every other vertex. So this one is connected to all of the other ones, this one is connected to all of the other ones, this one is connected to all the other ones, and so is that one. So that's what K5 looks like. And the way you know that you have the right complete graph is that you can't add any more edges without making it a multi-graph. If I added another edge to any one of these graphs, it would no longer be simple. So the complete graph is the largest simple graph you can have, where large refers to the number of edges in the graph. Any questions about the complete graph on n vertices? All right. So the next one I want to talk about is the cycle on n vertices. And for this, n has to be at least 3. You can't have a cycle with only 2 vertices. So this is this has the name C underscore N, where C stands for cycle. This has the vertices V1 through Vn, and the edges V1, V2, V2, V3, V3, V4, V5, V6, and so on, all the way until you get to the last one, and that's connected to the first one. So it has vertices V1, V2, all the way up to Vn, and it has edges V1, V2, V2, V3, V3, V4, and so on, all the way up to Vn minus 1, Vn, and then Vn, V1. Right, so it goes all the way around in the circle. So this is what it looks like. The smallest cycle I have is C3, and that is a triangle. So it looks like this. So as it happens, C3 looks exactly like K3. So those are in fact the exact same graph. But after that it starts to get a little bit different. So C4 is a square. C5 is a pentagon. And this pattern continues. Does this make sense? Right, so I'm drawing it to look nice, but the point is it has this number of edges in this kind of structure. So I mean, you could draw it to look like, I could draw it to look like this, and that is the exact same graph, because each vertex is connected to the next one, and the last is connected to the first. Typically, you want to draw it like this, though, because as we'll talk about probably next lecture, or maybe the one after, we don't like to have crossing edges. It's hard to reason about the graph when the edges cross because it's harder to make sense of. All right, so that's the cycle. The next one I'd like to talk about is the wheel. So the wheel on n is at least 3 vertices is called W sub n. And the way this works is you take Cn and add one vertex in the center and connect that to all the other vertices. So you take Cn, add one vertex that is connected to all others. So a consequence of this is that Cn actually has n plus 1 vertices, which is kind of annoying, but that's how I'm going to define it. Other textbooks don't define it this way, and it will instead say take Cn minus 1 and add a vertex. I suggest doing it this way, just in this course for the sake of consistency. So if I wanted W3, I take C3, which looks like this, and I add one vertex that's connected to all of the other vertices. That's what W3 would look like. Notice that it has 4 vertices, which is maybe a little misleading, but that's what the definition says to do, so that's what we do. W4 says, well, take C4, add a vertex in the middle, and connect it to all the other vertices. So that's what W4 is. W5 says take C5, add a vertex in the middle, and connect it to all the other vertices. So as you can see, as this starts to get more and more vertices, this looks kind of like a wheel with some spokes. Questions about the wheel? Yeah? Yeah, so these are going to come up later because we're going to start talking about properties that graphs can have. And one way we can understand those properties is by saying something like, oh, Cn has this property, no matter what n is, or maybe it's a function of n or something like that. The other reason is that a lot of the time when you're coming up with an algorithm for graphs, it's nice to test it on these things just because it's clear what they are. It's a good starting point for your testing. All right, so the last kind of graph I want to talk about now is kind of a weird one. It's not really like the other ones. I want to talk about bipartite graphs. So a bipartite graph, well, bi means two, and partite sounds a lot like partition. So bipartite kind of means a partition of size 2. That's how you can remember what it means. So a bipartite graph, G equals V comma E, is a graph such that V can be partitioned into V equals V1, into V1 and V2, with V1 and V2 having nothing in common, but when you take their union, you get back V. So this is something we've already seen, right? This is like with the equivalence classes. The equivalence classes partition some set. Well, this V1 and V2, this is a partitioning of the vertex set. And this partitioning has the property that every edge in the graph has one endpoint in V1 and the other endpoint in V2. So the edges always go from one part of the partition to the other part of the partition. And every edge in E has one endpoint in V1 and one endpoint in V2. So that's what it means to be a bipartite graph. In a few lectures, I'm going to talk about coloring graphs, and it turns out that this is kind of a similar notion. So if you imagine giving a color to every vertex in the graph, so let's say you have a graph, you color every vertex either red or blue. Well, being bipartite is like saying every edge is from a red vertex to a blue vertex or a blue vertex to a red vertex. You never have a red-red edge or a blue-blue edge. Right? That's the same thing as being bipartite, because then V1 is the set of all blue edges, and blue vertices, and V2 is the set of all red vertices. Yeah? Right, so in this case, we're talking about simple graphs. Other questions? All right, so that describes a general type of graph. I'm going to give a particular graph now. So the complete bipartite graph is called K, and K we sort of know is complete. And it has two indices, M and N. This is the graph that has one partition of size, so the vertex set is of size M plus N, and the partitioning is one part is size M, and the other part is size N. So I'll draw a picture if that's not clear. So the complete bipartite graph KMN has partitions of size M and N. And every element in one partition is connected to every element in the other partition. Okay, so let's do an example. So I'm going to draw K2, comma 3. So that means one partition has size 2, and the other partition has size 3. And now I draw an edge from this thing, which is in the top partition, to everything in the bottom part. So 1, 2, 3. And the same for the other vertex. This is connected to every vertex in the bottom part. And that is K2, 3. I don't need to do that again in the bottom part because the edges are all undirected. So this graph is K2, 3. Does that make sense? I'll do another one. Let's say I want K3, 3. Well, then I have 3 vertices on top, 3 vertices on the bottom, and the top ones are connected to everything. And I'm done. That's okay? Yeah? So you could do this the other way, right? Notice the bottom one, this one is connected to that one, and that one. This one is connected to that one, and that one. So just while you're drawing it, I like to go from top to bottom. You can go bottom to top, but the end result is the same.
And if any of the ones on top are connected to each other, it's the same bottom.
Right, because then you would have an edge between 2 vertices in the same partition. All right, so I'll do another one so it's clear. Let's say I have K5, 4. Well, then I have 5 vertices on top, 4 vertices on the bottom, and I do the same thing. I'll start with the bottom, say. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So these get quite messy quite quickly. And that's not too surprising because whenever you see complete, that means there's probably going to be a lot of edges. So it will probably be very messy. Yeah?
How can you tell just by looking at the
Right, so this is something that's a little bit tricky. When I've drawn it like this, it's hopefully obvious that there's a partition there, right? Because if you look at the top one, there's no edges between any 2 top ones. If you look at the bottom one, there's no edges between any 2 bottom ones. But remember that graphs can be drawn lots of different ways, right? I can draw this as a big jumble, and even if it has the same edges, it becomes very difficult to detect that it's bipartite. That is definitely an issue. We will address that a little bit later on in the course.
But I mean, like, so if there's a group of dots that are just not connected to each other, but other stuff, other dots, and by definition, that's a partition.
Right, so you have a partition when you can split the vertex set into 2 subsets, well, a bipartition, when you can split it into 2 subsets such that all edges go between subsets, never within a subset. Right? So you could do the same thing, you could split it into 3 subsets, and that's fine too. There's things like that, and we'll talk about that in the context of coloring. Other questions? Yeah?
So bipartite graph can never have a self-loop?
Right, because you would have to assign that vertex into some part, and by definition, the self-loop would go from that part back to that part. So again, we're only talking about simple graphs here. Other questions? All right. So the next topic we're going to talk about now is the idea of subgraphs. All right, so a subgraph of a graph G equals B comma E is another graph H. And notice that a graph is a pair of sets. So a subgraph, it would seem, that it would be reasonable to define it as another pair of sets where each set set in that pair is a subset of the original set. All right, maybe that's not an easier way of thinking about it, so I'll write out the definition and hopefully it'll be okay. So a subgraph of graph G is a graph H, and I'll call it H equals WF instead of VE, but of course it doesn't matter what I name these things, such that two things are true. W is a subset of V, and F is a subset of E. That's all that means. And just like with subsets, we have the notion of being a proper subset, we also have the notion of being a proper subgraph. So a subgraph H of G is proper if H is not the same as G. And two graphs are the same if their vertex sets are the same and their edge sets are the same. Right, so we look at both of those sets. Either of them is different than it is a proper subgraph. All right, so as an example, let's say I have K5. This is K5. I want to look at a subgraph of K5. So I pick a bunch of vertices that I would like, and I pick a bunch of edges I would like. So maybe I want this vertex, this vertex, this vertex, and this vertex. And maybe I want this edge. Maybe I want this edge. Maybe I want this edge. And maybe I want this edge. So to draw that out a little bit clearer, it's this, goes to that, goes to that, goes to that, which goes to that. So this thing here on the right is a subgraph of the thing on the left, because its vertex set is a subset of K5's vertex set, and its edge set is a subset of K5's edge set. Does that make sense? Yeah?
What happens if you pick an edge, but you don't pick a vertex that you can't get?
Right, so you have to pick both vertices that are on each edge. Yeah? That's completely fine. We're only interested in the connectivity of it. Yeah? If I didn't pick this right here? No, that's fine. The issue is if I tried to pick this edge, but not the other vertex. I'm not allowed to do that. Right? Because every edge needs two vertices. That is non-negotiable for graphs. At least these. Other questions? All right, so sometimes subgraphs are special. A subgraph is spanning if it contains all the vertices of the original graph. So basically you have to keep all the vertices in the original graph, but you're allowed to leave off edges. In that case, you'd be a spanning subgraph because the vertex sets are the same. That's what it means to be a spanning subgraph. Does that make sense? Okay, so we'll move on to the next topic about graphs, which is connectivity. So a lot of the time when you're working with graphs, what you want to know usually boils down to something related to are these two vertices in a graph connected? And the type of connectivity we're interested in is not if there's a direct connection. I mean, sometimes you want to know. But maybe you want to know if there's a bunch of edges between me, some vertex, and some other vertex. Right? So maybe, on the Facebook graph, for example, maybe you want to know if there's some series of connections between you and some other person. Right? Or in the Hollywood graph, you want to know what sequence of movies takes one actor to Kevin Bacon. Right? That's a path in that graph. It's a sequence of edges that visit the vertices in some way. So that's the question of connectivity. Sometimes we want to know if two vertices in a graph are connected. And the way they're connected is by a sequence of edges. And this sequence of edges will probably visit other vertices along the way, right? There might not be a direct connection between two vertices, but maybe I can detour through some other vertices. So there's lots of examples of this. Facebook graph, Hollywood graph. Let's say every vertex is some computer in a network, and you want to know, can two computers talk to each other? Well, is there a sequence of computers such that each one is connected to the previous one and the next one in the sequence so that it can forward messages from one computer to the destination computer? So what I've been getting at is the idea of a path. A path is a sequence of edges that begins at a vertex and travels from vertex to vertex along edges of the graph. That's all that a path is. So if I wanted to be more formal about what a path is, I can give you the official definition. So more formally, a path of length n, which has to be at least 0, from vertex u to vertex v in a graph G is a sequence of n edges, and that sequence is E1, E2, E3, and so on all the way up to En, such that the following is true. E1 is exactly where you wanted to start, and then it's some other vertex. E2 is x1, x2, where x2 is some other vertex. E3 is x2, x3, and this continues until I get to En, which is xn minus 1, v, because that's where I want to end up. So U is my starting point, V is my ending point. So is that definition of what a path is clear? This is the official mathematical one, so maybe I should specify. X1, X2, X3, all the way up to Xn are all somewhere in the vertex set. It doesn't matter what they are. Okay? And E1, E2, E3, all the way up to En, those are all in the edge set. Okay, so that's what a path is. We have a few special types of paths. So one thing you might notice is if the graph is simple, then it's enough to just use the vertex sequence to label the path. Why is that true? Yeah. Right, there's only one edge between two vertices. So I never have a situation where I could take one of multiple edges between vertices if the graph is simple. So if the graph is simple, you can think of a path as a sequence of vertices such that each vertex is adjacent to the previous one. That's the same. So if a graph is simple, then we can just use the vertex sequence. To label the graph. All right, we also have a special kind of path called a circuit. A path is a circuit if you start and stop in the same place. And a circuit is also called a cycle sometimes, which is maybe a little bit confusing because we have the cycle graph. This is separate. This happens if U and V are the same thing. So if your starting point and your destination are the same. Question? Sorry, yes, label the path. Label the path. Good catch. All right, so the path is a circuit or cycle if U equals V. We talk a little bit about the vertices and edges on that path. We say the path passes through all of those vertices. So x1, x2, all the way up to xn minus 1. And we say that the path traverses all of those edges. So the path traverses E1, E2, E3, all the way up to En. So you pass through vertices and you traverse edges. And we also have the notion of a simple path. A path is simple if it does not traverse an edge more than once. And usually we're interested in simple paths, right? So if you imagine that the vertices were the intersections of streets in the city, and the edges were if there's a street between those two intersections, and someone gave you directions somewhere, well, if you crossed the same street twice somewhere there, that would somehow be annoying, right? It doesn't seem like it would be a very good path. Questions so far? All right, so let's do some examples to get this terminology down a little bit. So I'm going to draw a graph. That's A, B, C. I'll do this the other way this time. D, E, F. I can go from A to B, B to C, C to F, E to F, D to E, A to B, and B to E, A to E, B to F, and from D to C. This is my graph. And I want to talk about this graph a little bit. So if I look at, so first we should note, this is a simple graph. So by this observation here, I can label a path just by labeling the vertices of that path, by specifying the vertices of the path. So one would be A, B, C, F, E. So let me show that to you. This is A, B, C, F, E. So the way I do that is by following this edge, this edge, this edge, and this edge. So, is that a path? Yes, it's a path. Is this a simple path? Yes. What's the length of this path? 4. Yeah, so this is one really important thing. The length of a path is the number of edges on the path. There are 4 edges on this path, so it has length 4. A very common mistake is to count the number of vertices you need to specify the path. There are 5 vertices on this path, but that's not the length. The length is the number of edges you traverse. Yeah? Oh, this is just an arbitrary example. This isn't the shortest path or anything like that. That's a different problem. So A, B, C, F, E is a simple path of length 4. All right. So let me do some more examples here. What about D, E, C, A? So let me highlight that for you. D, E, C, A. So is that going to be a path? No. So I can get from D to E, there's an edge there, but there's no edge EC. So that means that this thing is not a path. It's only a path if each vertex is connected to the previous vertex. So this thing does not count as a path. All right. What about B, C, F, E, B? So I'll highlight that. B, C, F, E, B. So is this thing a path? Is it a special kind of path? It's a circuit or a cycle, right? Mean the same thing. And I know that because it starts at B and it also ends at B. What's the length of this thing? Also 4, because I traverse 4 edges. I traverse the edge from B to C, from C to F, from F to E, and from E to B. So this is a circuit of length 4. Is this thing simple? Yes, it is. So in fact, I should have said simple circuit. It is a simple circuit of length 4. All right, so we'll do one more example on this graph. What about A, B, E, D, A, B? So A, B, E, D, A, B. Is this thing going to be a path? Is this a simple path? No. So why isn't it simple? Right, I go from A to B here and from A to B there. So this is not a simple path. So it is a non-simple path. What's the length of this path? 5, right? I go AB, which is 1, BE, which is 1, ED, which is 1, DA, which is 1, and AB, which is 1. So this is a non-simple path of length 5. So it doesn't matter that I traverse the edge AB twice, I'm still traversing that many edges. So it's not the number of unique edges traversed, it's the number of edges traversed is the length of the path. Yeah? The number of vertices? Okay, so is that going to work all the time? Right, so things break a little bit down for connectivity issues. Does anyone else have any thoughts about that? Okay, so that's a pretty good exercise. So ask yourself, if I list the vertices of a path, is the length of that list always one more than the length of the path? That's a good question. So you can consider that homework. All right, so a little bit more terminology now that we know this stuff. Now that we have the idea of paths, we're ready to talk about the idea of the graph itself being connected as opposed to two vertices being connected. So an undirected graph, and it's important that this is undirected. I'll talk about the directed case a little bit later. An undirected graph is connected if there is a path between every two distinct vertices in the graph. So for all pairs of vertices, which aren't the same vertex, is there a path between those? So at least one path, right? There could be more, and that's okay. So I'll show you some examples. So let's say we have something like this. Is this graph going to be connected? Yes, right? Pick any two vertices you like. Let's say this one and this one. And I ask myself, is there a path between those two vertices? And the answer is yes. It goes like this. So this thing here is actually indeed connected. Now that wasn't a proof because I only did it for one pair. I would need to do it for all pairs. But this is a pretty small graph, so hopefully you believe that I really can do that. An example of a graph that is not connected would be this. Right? This graph is not connected because if I pick this vertex and this vertex, there's no path of edges between those two vertices. I can't get from one vertex to the other. So this graph is not connected. And when something is not connected, we say it's disconnected. So that's an example of a disconnected graph. All right, so now that we have the idea of being a connected graph, let's look a little bit more at disconnected graphs. Question? Right, so we only need one example though, because remember the definition of connectivity is that all pairs have a path between them. Here's one pair that doesn't, therefore it's disconnected. It's also true that, this vertex here has no path to this one, and this vertex here has no path to that one, and so on. It's when you have one pair of vertices that have no path between them. Yeah. All right, so the different parts of a graph that are maximally connected are called connected components, and I'll describe what I mean by maximally in a second. The different parts of a graph that are maximally connected are called the connected components. So what this definition is trying to say in kind of a weird way is that this graph up here that's disconnected, it has two connected components, right? It just means those are the different parts of the graph. So what does maximally connected mean in this sense then? What is this trying to say? Yeah?
I'm sorry, I
Yep.
It said it's not connected with one pair of vertices
At least one.
that aren't connected.
Yeah.
But like in the graph on the left,
Yep.
a lot of two vertices are not connected.
No, they are connected. Remember, connected means connected by a path, not a direct edge. No, not necessarily a direct edge. Okay, so I haven't defined what maximally connected yet means, but given that I'm telling you that there are two connected components in the graph on the right, what does it feel like it means? Okay, so let's put it this way. Here's that graph. And why can't I say that the connected components are this? Why can't I say that there are three connected components? I mean, it doesn't feel like this graph has three parts, right? It feels like it has two parts. Why is that wrong? Yeah, two of the connected components are connected to each other, so they're not really connected components. They're really the same thing. So maximally connected means you couldn't add any, there are no connections between the connected components, between your supposed connected components. That's all maximally connected means. So if you do draw it like this, then that's wrong because this isn't maximally connected. And it's not maximally connected because of this edge. Okay, so this thing here, in fact, has two connected components. And I'll do them in green, say. One is this, and one is that. So any questions about connected components? Okay, so we'll move on. One special type of connected subgraph is called a tree. So I'll just say connected graph, but it often comes up in terms of subgraphs. One special type of connected graph is a tree. A tree is a connected, undirected graph that has no simple circuits. That's what a tree is. Okay, so I'll do some examples for you. This thing here is a tree. It's definitely connected, right? Another way you can see if it's connected is if it has one connected component. It's undirected because there's no arrows, and there are no simple circuits. So you can never get from a vertex back to that vertex with a path unless you cross an edge twice. That's what it means to be a tree. So, let me show you things that aren't trees but look a lot like this. This thing here, if I add an edge, let's say this edge here, this is not a tree because it has a simple circuit. So that would not count as a tree. And similarly, if I take this and let's say I deleted this edge, this would not be a tree because it is not connected. Is it clear what it means to be a tree? So trees are really useful because they come up all the time. They're very simple in structure, which is something that we like about them. So oftentimes, when we have a graph, what we want to do is find what's called a spanning subgraph that is a tree. And usually that's just called a spanning tree. And this is because trees capture all of the connectivity that the original graph had, but they have relatively few edges. Right? Trees have fewer edges than the original graph, often. So because a tree is simple in structure, we often want to find a spanning subgraph that is a spanning tree, or that is a tree. And this is called a spanning tree. So I'll do an example. Let's say we have some graph that looks like this. One thing you might want to do is find a spanning tree. So I'll highlight some possible spanning tree edges. There's definitely more than one answer for this. So I want it to be a tree, so I want it to be spanning. I want it to be both spanning and a tree. So spanning, remember, is that it has the exact same vertices. And tree means that it has no cycles and that it's connected. So I could take this edge, this edge, this edge, let's say this edge, that edge, that edge, that edge, and that edge. So if I look at just the highlighted yellow edges, that forms a tree. Does everyone believe that? So there's no cycles and it's connected. So that's what it means, no simple cycles. And it's connected. And this is spanning because the vertices in the tree are exactly the same as the vertices in the original graph. And we like trees because they're simple in structure. So notice if I wanted to check to see if two vertices were connected in the original graph, I could do that by checking to see if they were connected in the tree. And because the trees are simpler, usually this is faster. Does that make sense? Okay, so let's step back and talk about subgraphs in general again. So sometimes when you have a graph or a subgraph, removing a single vertex or a single edge might cause the graph to become disconnected. So somehow the graph is connected, but not by much. There's one vertex that if you plucked it out, it would become disconnected. So I'll define those two terms. A cut vertex is a vertex whose removal disconnects the remaining graph. Because when you remove a vertex, you also remove any edges incident on that vertex. All right. right, so we have a cut vertex. We also have the idea of a cut edge. A cut edge is an edge whose removal disconnects the remaining graph. All right, so let's do some examples so that we know what's going on. So I'll do a graph here. So this is A, B, C, D. This is E, F, G, H, like this. So this is my graph. What are the cut vertices of this graph? So, cut vertices. What are the cut vertices here? Yeah? E. Okay, so if I took out E, I would lose a bunch of edges, right? I would lose this edge, I would lose that edge, and that edge. So let's see what the graph looks like. If I take out E, the graph looks like this. And I think we can all agree that this graph is disconnected. So for sure, E is a cut edge. Okay, so let me put it back in. Any other cut edges? Yeah? C? Okay, so I heard B and C, so let's check each of those. If I took out B, this is what's left, and that's definitely disconnected because A has no path to anything else. So B certainly counts. And then the other suggestion I heard was C. If I took C out, then this is what results, and that's definitely disconnected. So C is also a cut vertex. B. So E, B, and C are cut vertices. Is there anything else a cut vertex? D. So if I take out D, I lose D, and I also lose these edges, but what remains is still connected. So D is not a cut vertex. What about A? Is A a cut vertex? No, because remember, I also lose the vertex, so what remains is still connected. So these three are in fact it. There are no other cut vertices. There's 3 cut vertices in this graph. Okay, and then the last thing I'd like to know about is the cut edges. What are the cut edges of this graph? Right, so if I take out the edge between C and E, the graph is disconnected. So CE is 1. Any others? Right, AB. If I remove the edge between A and B, then A is still there because I don't delete A, but the graph is disconnected because A is isolated. So AB is the other cut edge, and those are the only 2 in this graph. There isn't a third cut edge. All right, so next time we'll learn a little bit more about connectivity, and then we'll start looking at algorithms that work on graphs, which is where this gets interesting.